Hey everyone, and a big hello to all the BTech students tuning in. Look, if you've ever thought data structures are just something you have to grind through for interviews, I want you to stick around, because today we are going to break down one of the most important concepts out there, the binary search tree. This isn't just theory. This is a tool that will totally change how you think about writing fast, efficient code. So, to really get why the binary search tree is so brilliant, we first have to talk about a classic problem. It's the showdown. Arrays versus linked lists. Think about an array like a big numbered parking garage. If you know you're in spot 57, you can drive right to it. Super fast. But what if you need to add a car right in the middle? You have to get every single car after it to move back one spot. It's a total mess. Now, linked list solves that. Adding a new car is easy. You just change a couple of signs to point to it. But what if you need to find spot 57? Well, you have to start at the entrance and check every single spot until you find it. So you're stuck, right? You get fast searching or you get easy updates. You can't have both. Or can you?
And that leads us to the big question, the one that pushes computer science forward. Can we actually have our cake and eat it too? Can we build something that has that lightning-fast search of an array, but also the flexibility of a linked list?
The answer is a huge, resounding yes. But the solution requires us to kind of break our brains a little bit. We have to stop organizing our data in a straight line. The breakthrough happens when we start thinking hierarchically. We need to think in a tree. Okay, before we dive into the magic, we need to get the lingo down. It's super simple. Let's just quickly walk through the basic parts of any tree so we're all on the same page.
Everything starts at the top with a single point, the root. Think of it as the front door to our data structure. Anytime we want to find something or add something, we always start right here. So where does the actual data live? It lives inside of nodes. A node is basically just a little box, and it holds two things: the actual piece of data, like the number 7, and the directions or pointers to other nodes. And the lines that connect these little boxes, we call those edges. They're just the connections that show the relationships between all the different nodes. And finally, when you get to a node that doesn't have any connections leading away from it, that's a leaf. It's just the end of the line for that branch. And that's it. Root, node, edge, leaf. Got it? Good. Now for the really cool part. All right, so we take our basic tree idea, and now we add just one simple rule. And this one rule is what transforms it from a generic structure into the powerhouse we're talking about today, the binary search tree, or BST. Here it is, the secret sauce. The entire brain of the BST is on this slide. For any node you're looking at, if the new number you want to add is smaller, you go left. If the number is larger, you go right. That's it. That is the whole game. Lesser to the left, greater to the right. This simple logic is the key to everything. Let's just build one together right now. We'll start with a number 8. That's our root. Okay, next up is 7. Is 7 smaller or larger than 8? It's smaller, so it goes to the left. Cool. Next, 12. Larger than 8, so it goes to the right. Easy enough? Now it gets fun. Let's insert 2. We always start at the root, 8. 2 is smaller, so we go left. Now we're at 7. Is 2 smaller than 7? Yep, so it goes to the left of 7. See how that works? Last one, 5. Start at the root, 8. 5 is smaller, go left. We're at 7. 5 is smaller than 7, go left again. Now we're at 2. Is 5 smaller or larger than 2? It's larger, so it goes to the right of 2. And just like that, every number has found its one perfect logical spot. Okay, so we've built this cool-looking structure. So what? What's the point? Well, this is where the BST performs its real magic trick. It has this way of reading the data back out, and the result is honestly brilliant. This trick is called in-order traversal. And the logic is so simple, you're gonna love it. We just apply the same rule over and over again to every node in the tree. The rule is always, first go as far left as you can, then visit the node itself, and finally go right. Just remember that. Left, root, right. And here is the payoff. This is the moment it all clicks. When we apply that simple left, root, right rule to the tree we just built, what do we get? We get 2, then 5, then 7, 8, 12, 15. What is that? It's a perfectly sorted list. Out of what looked like a random jumble, this simple rule pulls out all our data in order every single time. It's just so cool. Now this is why your future boss will care. This is the so what. If you had 10,000 items in a plain old list, to find one specific item, you might have to check all 10,000. But in a balanced binary search tree, how many steps does it take? About 14. Let that sink in for a second. 10,000 versus 14. That's not just a little better, it's a completely different universe of speed.
So you can see, this is more than just a clever idea from a textbook. Why is this a total game changer for your career? Why do companies from startups to Google expect you to know this stuff inside and out?
Well, it's simple. In the real world, speed is money. Every nanosecond a processor spends searching for data costs something. By using a structure like a BST, companies make their databases, their search functions, their file systems, everything, orders of magnitude faster. That saves millions. And that, right there, is why this is guaranteed to come up in your technical interviews. They want to know if you can think efficiently.
At the end of the day, it really all boils down to this one simple truth. You can have the most powerful computer on the planet, but if your data is organized poorly, your program will be slow. How you choose to structure your data is everything.
But there's always a but, isn't there? We kind of got lucky. The numbers we used made a nice, bushy, balanced tree. What if we had inserted them in order? 2, then 5, then 7, then 8. Well, each new number would just go to the right of the last one. We'd end up with this long, stringy chain. We wouldn't have a tree at all. We'd basically have a glorified linked list, and all that amazing search speed would just vanish. This problem, the unbalanced tree, is a huge deal. And the solutions, things like AVL trees and red-black trees, are what you'll learn next to become a true master. But that's a story for another time.